Okay? Can you hear me?
Yes, okay. It's okay.
Good.
Yes.
All right. So let me get my pointer here. So we have seen so far essentially one scattering process, which is electron phonon scattering. So now we have to move to other scattering processes which are important in controlling the charge transport in semiconductors and semiconductor devices. And things get more interesting because we're moving away from, at least in some of these cases, from the ideal pure lattice that we have considered so far. So today we're going to talk about ionized impurities, mainly dopants. It's a scattering process, which of course is very important because one of the major benefit of semiconductors is given by the word semi. We can dope them, so we can create junctions and devices. Related to that are some effects which are due to Coulomb interactions among particles, so we'll have to deal with that. These two are extremely complicated topics. Although scattering with impurities, with the dopants, is usually treated in a relatively simple way, the more you think about it, the more complicated it gets. And I'll try and give you a flavor for the many approximations that we have to make in order to deal with the problem. And recent and not so recent advances in understanding what is the role of effects which are neglected by the usual approximations. Coulomb interactions among electrons is a huge issue. Even in a homogeneous electron gas, it has been one of the major problems that people had to face, particularly because of exchange and correlation energies and how to treat them. I will briefly mention also one particular aspect of particle-particle interaction, which is impact ionization, which is important in devices. I'm not sure if today I will be able to conclude this section talking about radiative transition, so interaction of semiconductors with light, talking mainly about the absorption spectrum of the material. So this will be the section that maybe we'll conclude today, maybe we'll finish it up next week, before moving to transport per se, which we have put it in red here as something that we have to yet to be dealing with. So starting from the quantum equation of motion for a system of electrons in a crystal, and then see how we can treat the problem in a semi-classical way. Okay, so let's start with impurity scattering. I just added a few minutes ago a reference to an old paper, which, however, I think is very nice. It's kind of dated, some 40 years old now, by Chattopadhyay and Hans Weisser, that discusses the issues, the many issues that we have to deal with, dealing with electron scattering with mainly dopants, and that's what I mean by ionized impurities. So the problem is quite complicated. So I tried to express it here and elucidate it a little bit in a cartoon. So the blue balls here are silicon ions that keep silicon to fix the ideas, and the red dots are the impurities, the dopants that we have placed. And we want to know what happens to, in an ideal case, a plane wave, which is represented by these vertical bars, which has the wavefront of a plane wave, a block wave, which is coming from the left and propagating to the right. And of course, if the crystal were ideal, this would be just a block wave, which propagates with whatever conductance is given by the band structure of the material. So pure propagation, no reflections, no nothing. But now we replace silicon with some different ions, and these ions can be lighter than silicon. For example, boron, which is one of the most commonly used, well, mainly in the past because it diffuses fast, p-type semiconductor, an acceptor, dopant. They can be roughly the same mass as silicon, like phosphorus, which used to be the common dopant for n-type silicon. They can be much heavier, Recently, in the past 20 years, the word recently shows my age when I talk about 20 years as recent. One of the issues as being in scaling electronic devices is limit the diffusion of the dopants, because of course you want to scale all the dimensions of the device, so also junctions have to be reduced in width, and this requires ions which are much bigger because they diffuse lower, and so one can control their position in a better way. So we have a different ion here with a different mass. Lighter, roughly the same mass as silicon, much heavier, like antimony, like indium, like arsenic, which are used for PNN type doping. So there are lots of issues that we have to deal with here. The electron, this plane wave comes, and of course the impurity, this dopant, can move around. So I've written here the Hamiltonian that describes the interaction of an electron, described in second quantized form, if you want, by the electron density. Psi star psi in conventional quantum mechanics will be the electron density multiplied by a charge. And here is the potential energy for the scatter, given by the scatter. And we have impurities at position r sub I. I is the index that labels the various dopants. And we have to sum over all of them, and then there is a normalization volume over here. And these guys can move. The position of each impurity can move. And there can be two types of motion. One would be they will vibrating according to phonons which are propagating in silicon, so silicon phonons. But there's more. There will be also localized phonons. Suppose that I have boron here, which is lighter. Boron can oscillate when hit by an electron at some higher frequency than what the frequency of the phonons in silicon would be. So clearly this frequency mismatch means that a phonon, so to speak, originating from the boron will decay exponentially away from the location of the dopant because of the mismatch of frequencies, so we'll have evanescent waves. The same would happen when we have a heavier ion in which the frequency of the oscillation will be much lower than the frequency at which the silicon ions would want to vibrate. So in principle, we will have to deal with scattering theory, what happens to a plane wave which is scattered by a Coulombic potential. These are positive or negatively charged impurities, usually one ionization, because we're using for silicon group 3 or group 5 elements, so they would have one fewer electrons or one more electrons than silicon. So they would give the electron or take it away, so give a hole to the lattice and remain positively or negatively charged. So we would have Coulomb scattering between these plane waves and the Coulomb potential attractive or repulsive of the impurity. The impurity may move. We don't have a single impurity, so we would have to go a little bit beyond scattering theory that is dealt with in quantum mechanics, because we may have scattering with centers, and there will be a coherence between scattering from one impurity to the next. For example, the plane wave which comes here will be reflected by the first impurity. This reflected wave will reach the second impurity, and there will be an interference between the plane wave, the block wave, which is incident, and the scattered wave from the first impurity. So scattering with the second impurity will be affected by the distance between the two impurities, the phase, the angle of the way which is scattered by the first impurity, which essentially says that we have to go beyond the first Born approximation. So this is extremely complicated. Regarding the fact that impurity can move, one should notice that this would make the scattering process, strictly speaking, inelastic. Of course, the impurity has a much heavier mass than the electrons, so the recoil will be very small, but the energy could lead, the energy of the localized phonon or a phonon coupled to the bulk phonon of the material would lead to resonances, to exchange of energy between the incoming electrons and impurity. Another possibility of having an inelastic process would be accounting for the fact that impurity may have, beyond the possibility of moving, some internal degrees of freedom, the electronic states of the impurity. This may be an important effect when the impurity actually is not ionized, such as in freeze-out. If you go to very low temperature, the impurity level has a depth which may be bigger now than the thermal energy at sufficiently low temperature. So the impurity will not be ionized. And for example, there are lots of papers dealing with the effect of impact ionization in impurities in the freeze-out conditions. For silicon freeze-out, even in heavily doped silicon, say 10 to the 20, is at very low temperature, but about 20 Kelvin or so for, I think, 10 to the 19 per cubic centimeter. So at low temperature may be interesting, but at room temperature or higher temperature, which is the temperature which a chip operates, this will not usually be an issue, and exciting core levels or valence states from the impurity clearly requires energies which are beyond what we're interested in transport. Nevertheless, one should worry about the fact that impurity may have some degrees of freedom, and so the process would not be reversible, time reversible anymore. So the usual approximations are: ignore the fact that these guys move, that the impurities move. So freeze the position of the impurities at the equilibrium position of the lattice. The impurities are clearly substitutional in order to be electrically active and contribute to doping. They do not move. There's quite a bit of work. I list here just a few references if you're interested about people have worried about this. I think roughly in the 1960s and then later on, papers were published, have been published almost periodically about what is the effect of bulk phonons, assisted processes. And the idea is that these are negligible. But the considerations, the approximations made in these papers, which I think are the grounds for ignoring these phonon-assisted processes, is that they dealt with bulk phonons. I've not found anything regarding the possibility that the localized phonons, by the way, the existence of localized phonons is another big issue, and you will find many papers in the literature, that localized phonons may assist the process. So we'll ignore this, assuming that the one phonon processes are negligible, and they do contribute much to significant corrections to the scattering rates of the cross-section that you might have. So we'll keep them fixed. Keeping them fixed is an interesting issue because well, it has some benefits, if you wish. It gives us now a reversible process. Think about Coulomb potentials, which are frozen here. Again, we'll ignore the possibility that these impurities may move. The process is purely elastic now. If we freeze the impurity in a lattice, the mass of the scattering center now becomes the mass of the entire crystal, which is the mass of the chip, if you wish. If we ignore phonons altogether, the chip is bonded, is fixed to a board, which is in your computer, on your phone. So it's a huge mass compared to the electron. So the recoil of the impurity, which is of the crystal, can be neglected. Again, under the assumption that we can ignore the motion of this impurity. So given this situation, the process can be solved by solving Schrödinger equation. It's a scattering problem which you have a plane wave, okay, a block wave in this case, and we can just look at the potential, which is the sum of the potentials of the impurities, if we know where they are. So it's a known position of the known configurations of the impurities, and of course we can solve it using conventional quantum mechanics as a scattering problem, and that would be purely reversible, no dissipation. We'll talk in the next slide about where dissipation may come from, essentially from our ignorance about where the impurities are, or from possible multiple configurations of the impurities. So we'll soon ignore this effect. As I said, in this picture, right, in the Hamiltonian this way, there are lots of things that we are hiding under the rug, no internal degrees of freedom for the impurities, no motion of the impurities, and also depending on what we use here, okay, I put the Schrödinger field here in second quantized form, but in calculating the matrix element, we will use the apr30 wave functions. We also imply, in writing it this way, that we're using the firstborn approximation. And this may lead to some corrections that have been studied. So it's a very complicated problem. So the main simplifications we're doing now is the impurities are considered to be scattering centers with fixed position, purely Coulombic potential. The ionization of the impurity is typically taken as 1. It can be attractive or repulsive, depending whether we're dealing with donors or acceptors in N-type doped silicon or P-type doped silicon, vice versa. And the problem is beginning to be manageable. So let's move on. This is just a cut and paste of the part 1, part 2 that I posted on the class, whatever it's called, supplemental material or whatever. The collision is considered to be elastic and reversible as well. Usually elastic collision are reversible again because there's no exchange of energy, but the main thing that distinguishes time reversible from time irreversible processes is whether we lose memory of the phase, whether we dissipate the phase. So in the following, I will use often the word dissipation. I don't really mean necessarily energy dissipation, but the fact that the process is irreversible, so we lose knowledge of the phase. For example, if we consider a localized phonon as a process that can assist the scattering event, if we don't keep track of what the phonons do, we erase some information from the system, and we cannot go back in time because we don't know the phase or the exact momentum, if you wish, of the phonon that has been emitted or absorbed in this phonon-assisted scattering process. So, as I said, this is a purely reversible scattering process described by this Hamiltonian, which is the main difference between these processes and the electron-phonon interaction. Again, in principle, you can solve exactly Schrödinger equation with the electron-phonon interaction for the entire crystal. We don't do that. We typically assume that there is a big thermal bath, so the information of the phonons which assist a particular process is lost. And this process of erasing information which causes irreversibility. In impurity scattering, clearly, if we assume that the process is purely elastic, which is the discussion that this mumble jumble that I hear, if we assume that it's elastic, then irreversibility comes from another consideration. I'm not aware of any paper before the work that Kohn and Luttinger did in late 50s. They essentially considered the Hamiltonian that I wrote here. They plugged it in by using Green's functional techniques, but that's just a method to approach the problem. They plugged it into the equation of motion for the distribution function of quantum mechanics, which is called density matrix. We will discuss it probably next week. And they show that actually you can introduce irreversibility provided you take an average, call it ensemble average, maybe I could call it configuration average, in which they consider a large chunk of semiconductors, and they look at what is the average distribution of the impurities among various sub-blocks, sub-elements of this lattice. It amounts to a random phase approximation, which also permits us to ignore the coherence between multiple scattering processes. As I said, the one issue that we have to worry about is essentially going beyond the firstborn approximation, looking at what is the effect of the fact that the wave which is incident on the second impurity here is actually not the original incident block wave, but it's a block wave plus the wave which is scattered by the first impurity. Again, the firstborn approximation is actually more strict because it even ignores the reflected wave from the first impurity. So we don't have to worry about that. Essentially, it's because if we don't know where the second impurity is, if we take it as a random distribution of the second impurity with respect to the first, all the possible interference effects that we might have will wash out because of destructive interference, and constructive interference will average out to no interference at all when we take a random configuration of impurities. So what this boils down to is this sum over potentials is actually taken as an average by multiplying the scattering with the scattering process, the Hamiltonian, which expresses the interaction with the single impurities, multiplying simply by the density of impurities that we have. This is a tricky process. Again, these papers are not easy reading, but they're in the 50s, actually, there was a flurry of papers dealing with the problem of reaching the Boltzmann transport equation that we will discuss in the next section of the class, studied from a quantum approach to transport. Kohn and Lattinger did the work regarding impurities. There were several other papers, notably among them a paper by Leo van Hove and Argyles as well, that deals with general interactions and what is the set of general properties that the perturbations must obey in order to lead you to irreversibility and the fact that you can reach a semi-classical Boltzmann transport equation in dealing with transport of electrons in a solid. So the impurity potential now, the Hamiltonian that describes the impurity now is just the per unit volume, is just the Hamiltonian you would have for scattering of a single electron with an impurity, average overall impurities, and then you multiply by the density of impurities that you have. So now it's simpler, it's easier to deal with. Here, again, depending on what we use for Xi, we can use the first-born approximation or worry about additional corrections, but it's a manageable interaction. Essentially, it's a Coulomb scattering process, a Rutherford scattering process using the classical terminology for each impurity. And that's what we usually do. So we take the bare potential for the impurity that we have, which is, again, this Z is the ionization number of the impurity, which we usually take it as 1, which is the case in almost all the situations that I can think of. The Fourier components of the Coulomb potential are just 1 over q squared. And then we can follow the same procedure that I described before with dealing with generalities of scattering of block electrons in a solid, following the same procedure, and we can write the matrix element, if you recall, in this way, where this was the Fourier transform. So essentially this term, which would replace q with k minus k prime plus g, and this overlap factor, which is the correction that we must have to a purely plane wave free electron model when we move to a crystal in which the plane wave is replaced by a block wave. So we have to worry with the little u's, the periodic component of the block function. So we can use essentially the same process. Notice again that since we're using block waves to express now our matrix element in terms of the Fourier components of the scattering potential, we're essentially using the first-born approximation, which again, I remind you, the first-born approximation says, well, the incident wave is impinging on the scatterer. However, the scatterer reflects a portion of the wave. So the incident wave is actually the sum of the incident wave and the scattering component. We'll ignore the latter. Second-born approximation will be the first iteration, the first correction beyond that. So in principle, we may think of replacing the psi's with some of these u's and these plane waves with scattered waves, which you get from whatever order of the Born approximation we're using. But here we will stick to the first Born approximation. So all we have to do is replace this potential, the Coulomb potential, with in these expressions that we have, plug it in here, and then calculate the scattering rate. Easily said, not so easily done. Just to express the Hamiltonian in second quantized form, you realize what this process means. We have an electron with wave vector k coming in. It scatters with some vertex, how we say it, vq. And if you wish to account for the overlap integral of the block function, there is a correction. And you generate another electron which scatters with a given momentum q, so it's a given angle. And of course, we have the possibility of having normal processes, or processes in which the electron is carried to the next Brillouin zone or the next again. And so we have to sum over all possible wave vectors of the translation vectors of the reciprocal lattice. You realize immediately that since we have a q-squared dependence here, as we add the bigger and bigger g's, the interactions gets weaker and weaker. So typically UMCAL processes do not matter too much. Same as intervalley processes don't matter too much because we have to go from a k to a k plus q, where q is sufficiently large and the strength of the potential is weak. So we can write it this way, in simple form, ignoring this overlap factor that for now we'll ignore, so we'll treat it as the electrons as plane waves, purely plane waves. Good. So let's just do the algebra here and see what happens. I think that the main conclusion should not be a surprise. So we use Fermi-Golden rule. I'm a little unsure what is the correct terminology. Here, people usually say either first-Born approximation or Fermi-Golden rule as synonyms, interchangeable terms. I view it differently. In the approximation that we use so far, our scattering potential is time independent, so we really have to use the first-Born approximation. The expression is identical, so this justifies the use of these two terms as synonyms. But strictly speaking, we're using the first-Born approximation. So there's nothing time-dependent here if we ignore, as we said before, the possibility that impurity moves and we have a phonon-assisted bulk or localized phonon-assisted processes. So we use the first-Born approximation. Let's call it Fermi-Golden rule with this caveat that I gave you. So the matrix element is just this object that I wrote here. I kept the z just for the heck, but clearly this is equals to 1. These are the prefactors that we have out of taking the square of v sub q. And then we have a q to the 4th power in the denominator, which is coming from any square this term, and the energy conservation, because we are dealing with a process which we're assuming it's elastic. So we can go from Cartesian coordinates here, we can express the integration over spherical coordinates. The integral over the azimuthal angle is simply 2 pi, which gets rid of the 2 pi that I have here. And we're left with the integral over the polar angle and the wave vectors. So we can usually do the well-known tricks to deal with the delta function. We replace the coordinate sine theta, or better yet, this object over here with the prefactor over here in this expression. So we can perform the integration over the polar angle in a relatively simple way, and this is what we get. Notice that the extreme of integration, the limit of integration, the upper limit is 2k, because this is the maximum wave vector that an electron can transfer to the lattice, so to speak, with for a head-on reflection, so full reflection at 180 degrees from the incident direction. So we can simply plug this now into our expression for the scattering rate. These are all the constants that we get out of having squared the Hamiltonian. And of course, we find that we have a nice expression that diverges at small q. Again, this should come as no surprise that we get infinity. Even in classical mechanics, rather for scattering gives you a differential cross-section that we can calculate, but the total cross-section is infinity, diverges. And the reason is extremely simple. We're dealing with a long-range interaction. Essentially, what we're dealing is considering in dealing various R's or various radial dependence on the potential. When we have an impact parameter which is given by some parameter b, the potential will go as 1 over b. But the total, the thickness of the shell that we have coming from the scattering impact parameters will grow as like b. We integrate over all impact parameters b from 0 to infinity, and we get infinity. So it's well known that the Coulomb interaction is long range and the cross-section will be infinity. So how do we fix the problem? How do we deal with this? I mean, I wouldn't call it a problem. I mean, it's an obvious result from having to deal with a longer range interaction. Of course, you can argue that the crystal is finite, that there is a limit to the range that I have, but still we will get extremely large numbers if we consider the lower limit of integration as 1 over the size of the crystal. Historically, there have been two ways. I'm not sure why I flipped the two, but they're roughly the same time. The first approach was historically due to Conwell and Weisskopf, and the second one is given by, it's called the Brooks-Herring model. Actually, the original paper was authored only by Brooks. Anyway, so we have to somehow truncate the range of interaction. At long distance, it means we go to small q. So we have to put a limit to the 0 over here, because that's a singularity that we get, right? We get 1 over q squared here at q equals 0. So we have to put some lower bound to the integration here. It's what sometimes is called an infrared divergence, meaning long wavelengths. So the Brooks-Herring model says, well, we're dealing with scattering with dopants. Typically, unless we deplete somehow the material, there will be a density of free carriers for a neutral system will be just equal to the dopant density. These free carriers, as we've seen, screen statically the scattering potential, which means, let me go to the picture here. If this impurity is a donor, say it's phosphorus, for example, it has charge +1. If we have silicon which is doped at, say, 10 to the 19 dopants per cubic centimeter, if we're using an unbiased charge neutral chunk of crystal, there will be 10 to the 19 electrons per cubic centimeter, and they will go and screen. It will be attracted by the impurity. So a plane wave which is coming from far away at large distance will not see any charge. It is only a short distance it will begin to see the charge of the impurity. So this is Thomas Fermi screening, or Debye-Hückel if we're not in a degenerate situation. So we can simply express our potential now as a screened Coulomb potential, which implies that we replace the q squared in the denominator of the scattering potential, its Fourier transform, with q squared plus beta squared. Beta, I remind you, is the inverse screening length. This could be the Debye-Hückel screening parameter or the Thomas Fermi screening parameter that we saw, forget when, a few lectures ago. So now the integral is not diverging anymore. The troublesome lower limit at 0 doesn't give us any problem because we have the screening. Essentially, it tells us that at long distances, the potential goes to 0 exponentially, as it happens if you take the Fourier transform, or the inverse Fourier transform back to real space of the scattering potential. And we get an expression, which is the well-known expression of the Brooks-Herring approximation. So that's one way to fix the problem, the divergence problem of the infinite cross-section or the infinite scattering rate that we get. Notice that this depends on the energy, at high energy. This essentially is proportional to the energy of the electron. This is proportional to the square root. So you see that at large energies, the scattering rate goes like 1 over the square root of the energy. We saw that before. This is the typical result of Coulomb interactions, as I told you. There is some power of Q in the denominator, so the energy dependence will be such that at small energy, you're dominated by the density of states. At a high energy, the density of states grows like the square root of energy, which is essentially this term here, but the matrix element or the scattering potential gives you an energy denominator. So like all Coulomb interaction, after an initial increase due to the fact that the density of states goes up as the energy of the incoming electron increases, at large energy, the electron feels a smaller and smaller interaction in relative terms, relative to its energy. So this is the first approach, the Brooks-Herring model. Actually, historically came a year after. Conwell and Weiskopf developed another model. And the Conwell and Weiskopf model instead says, well, here, the problem that we have is, as I mentioned before, we're integrating over all impact parameters. And the problem comes when we look at the impact parameter, which is very large. The impact parameter, by the way, is if I have an impurity, we go back here, is we have clearly, this is a plane wave where it doesn't, but it's an idealized situation. If we have a wave packet propagating over here at this distance from the impurity projected along the direction of propagation, you see that we're integrating over impact parameters can go from very small. At 0, we had head-on collision. At very large impact parameters, we're far away from the impurity. And it is at large impact parameters that the problem arises. So, is it a realistic situation? Well, no, because if we go to very large impact parameters and we're considering one particular impurity, there will be another impurity which has a smaller impact parameters. So it's something that Ridley would later call statistical screening and refine the object. Conwell and Weiskopf said, let's chop the impact parameter to the average distance R0 between the impurities. There are many ways to do it. Either define it this way, we take the volume surrounding an impurity of a sphere of volume 4/3 pi times the cube of this sphere, and the cube of the radius of this sphere it will give you the volume surrounding each impurity. 1 over this will be the density of impurities, which gives you this value for this, how would I say, it's not the average, really the average impurity distance, but something related to it. Okay, so what we do is in taking the Fourier transform of the Coulomb potential, rather than having a simple 1 over q square, with something which kills it. Notice that the q goes to 0, this goes like q squared or 0 square. The q square over here cancels the singularity that we have here. So essentially we chop the range of the Coulomb potential to this average inter-impurity separation. And we can do the algebra now. The integration over q now is again regularized by the presence of this term. We can perform the integration as we did before, and notice that we get a scattering rate, which is of course proportional to the density of the impurities, if you wish, to the ionization square, but we set it usually this to 1. And notice that this is essentially independent of density, because roughly or very weakly, because this term is proportional to 1 over the density. So there is a weak dependence of density, contrary to what happens in Brooks-Herring model. So this, I think that the fact that there are these two models, if you want, and criticize some of the approximations that have been made, you will be justified, and indeed lots of people have done so. The agreement between the mobility calculated using either of these methods sometimes works, in some situations doesn't quite work. In some materials it may work well over a wide range of density, in other materials or different types of situations. For example, in high electromobility transistors, when you have what's called a delta doping, you dope the barrier material, and the electrons that spill over give you the electron density in the channel. So scattering now is removed between the electrons which are scattering with centers which are removed from the channel themselves. Neither of these methods worked terribly well. And even in silicon and high doping, there are lots of issues that I'll mention later. Heavy doping is a big issue, and indeed we'll visit it again when dealing with electron-electron interaction. So these are two, I could say, popular models to deal with impurity scattering. Ridley tried to merge the two. There is actually good reason, which was given by Jerry Mann in this wonderful paper that deals mainly with bandgap narrowing in heavily doped materials, but the discussion is more general than that, and I will mention it again more than once. Ridley said, well, there are some situations in which the Brooks-Henry model is better than the Coleman-Weisskopf model, and vice versa. Mahan actually shows that he did some variational calculations to look at what is the wave function in a crystal with a random distribution of impurities. And he found out that, so there is an inconsistency here very often, if you notice. I will mention it again later on. The Brooks-Henry model tries to, as people say, have a cake and eat it too. You can have it both ways. The electrons, so you have the system, you have the dopants, you have an equal concentration of electrons, and these electrons are supposed to screen completely the impurities. In particular, I will mention again something that I didn't talk about, which is Friedel's sum rule in screening. You want a number of electrons equals to ionization of the impurity per impurity. So all of the electrons are taken by screening the impurity. Yet, you use the scattering rate that you calculate using the Brooks-Henry model to calculate the mobility, where all electrons move. So which is which? Do they screen or do they move? Clearly, they cannot all do the same things. There will be some electrons which don't move that much and they screen well, electrons that move and they don't screen that well anymore. So you cannot double count it. And he found out that at low density, that's okay. If you don't have that many electrons, the Brooks-Henry model is not too bad, or more than the Brooks-Henry model per se, the approximations or the assumptions made to screen the impurity potential is okay. But if you go to high densities, then the double counting issue becomes to be really serious, and it leads to errors. And actually, the Coleman-Weisskopf model should, in principle, give a better description of the physics. How do you merge the two? And this is something that Brian Ridley did, as you say, in 1988. He tries to merge the two approaches, and he has an expression which takes the Brooks-Henry model, the scattering rate, or here's the scattering time of the Brooks-Henry model. This D is the average the distance between the impurities. This is the group velocity of an electron momentum, K. And you find out that the scattering rate can be expressed in this form. And essentially, it gives you something that merges the Brooks-Henry to the Coleman-Weisskopf model. Ridley applied this to the case that I mentioned before, which is impurity scattering, remote impurity scattering in high electron mobility transistors. It was an issue because mainly it was, say, indium gallium arsenide with an aluminum gallium arsenide barrier and the delta doping in the L-gas barrier layer. Using either Coleman-Weisskopf or Brooks-Henry in this two-dimensional transport situation led to bad results compared to experiments. And the claim was that this expression works best in that case. In my experience, I've tried to use it in a few cases for silicon. It doesn't quite work as well as it should. So I'm not sure if this is a particular situation in which the method works, if I implemented it incorrectly, but it doesn't seem to improve much the situation. It's however, a clear indication that the problem is more complicated than we make it, usually, than we approximate it, for various reasons that I will describe in a minute. And that's what we have to deal with. So there's lots of additional corrections. I think that I mentioned before several of them. The Born approximation, for example, we are stuck to the first Born approximation. There are corrections that one may think of, and indeed this is something that I worked on because there was a paper that claimed that the mobility is affected by the atomic species that you have. In principle, it would make sense. If I use as p-type doping boron instead of, or indium, for example, which is a much bigger item, clearly there would be something that leads you to believe that the scattering cross-section will be different. Indeed, there is an effect that has never been considered in the papers that I've seen, which is indium is a big ion, so there will be some local distortion of the lattice. Local distortion would imply a local strain. So you may have something similar to a deformation potential interaction when you put a big ion in a crystal. I'm not sure. I haven't seen any paper that deals with that, but it would be interesting to look at what is the effect. But there was a paper that claimed that just the presence of a different impurity, forgetting the distortion of the lattice around the impurity, can be probed. Now, the issue is a little bit serious. At sufficiently high energy, an electron will have a wavelength which will be short enough to probe what happens very close to the nucleus. And so, indeed, you can tell the difference between phosphorus and indium, for example, or boron and indium, or phosphorus and antimony, for example. But in general, these energies are much larger than what you have when you're dealing with mobilities, for example, or even transport up to a few tens of an electron volts in devices. So I was looking at what is the correction that you might expect. A correct way to deal with it would be to say, well, let's start by taking our silicon, let's pluck away a silicon ion and replace it with a dopant. It might be, in this case, I consider, for example, a few dopants. The scattering potential that you would have would be simply given by the Coulomb potential, and then something which is related to the size of the ion that you have. This sigma I is a fit which you may obtain from some Hartree-Fock calculation of the atomic structure of these 4 or 5-fold ionized ions, 3 or 5, depending whether you're using N or P silicon, and replace this potential, the silicon potential, with this potential. So you replace it, you take the potential that you had before, take it away, that's for silicon, you replace it with the potential due to the impurity, and this will be your perturbation potential. Then you screen it. Notice that valence electrons can contribute, and indeed there are several models. I use here a particular model for the momentum dependence of the dielectric function of the valence electrons, and having screened it, you can find what is the potential that you would have if you did this replacement. And the situation is that, sorry, mistake here, that the effect that you have is extremely small. There is very little that can let you, little effect that can permit you to distinguish the mobility between p-type silicon doped with boron or indium, for example, or n-type silicon, phosphorus, and arsenic. So you have to go to higher energies. This is something that is sometimes called related to what is called central cell corrections, which may have to do with instead with the distortion of the lattice, because this clearly will happen if you dope silicon, n-type silicon, with antimony rather than phosphorus. Clearly there will be some distortion of the lattice around the antimony because it's a big ion, and so this may lead again to some deformation potential like component of the scattering potential. Another problem is, let's talk about what I write here. Another problem is that the first Born approximation that we've used does not distinguish whether the big Z, the charge state of the impurity, is positive or negative, +1 or -1. There's nothing to distinguish the two. In principle, you would expect that there is some difference. In particular, if you go and look at minority carrier mobility versus majority carrier mobility. What I mean, for example, is electrons scattering with positively charged centers as n-type silicon. Electrons are negative objects, the donors are positively charged. In principle, we expect that the wave function will be attracted a little bit by the scattering center, and so the cross-section may be larger. Then what you have, for example, is if you're dealing with electrons which are moving in the base of a bipolar transistor. In that case, the electrons are moving in p-type silicon, they are minority carriers. The impurities now will be repulsive. they will be also negatively charged. So you expect the wave function of the block wave function perturbed by the impurity will be pushed away from the scattering center, so the cross-section will be reduced. The overlap between the wave function and the scattering center, but the potential will be reduced. The first Born approximation assumes that the incident wave is unperturbed. It stays the way it is. It's only the corrections that you get from going beyond the first Born approximation. So looking at what that the incident wave actually is composed by the original incident wave plus the scatter wave, only that can give you some corrections. One way to deal with the problem is to use, I'm not sure if you saw it in quantum mechanics, a method to calculate cross sections in scattering theory, which is given by phase shift. You expand your wave function, which is a plane wave in the ideal scattering problem that you deal in quantum mechanics. Rather than keeping it as a plane wave in Cartesian coordinates, you expand it into spherical harmonics. And then you calculate the shift that each angular momentum component of the spherical harmonics has, and you can calculate it with expressions which are similar to the Born approximations at various orders. And for the phase shift, you can calculate the cross-section. And you see that indeed in this case, majority and minority carrier mobilities can be different. The scattering rate between an attractive and a repulsive center will be different. Bennett and Loney have, I think, spent their careers working with this. So they went through travels. I don't remember exactly the order of the phase shift they considered, but something like 30, 40. So a tremendous algebraic effort, all done by hand, to calculate these phase shift corrections for silicon, for germanium, for even polar material like gallium arsenide. So I list here one paper, but there's many more about that. Related to that is the fact that if you look at Brooks-Haring, the Thomas Fermi-Debye-Huckel screening, you expect that the impurity, if you integrate over all volume, for an isolated impurity, integrate over all volume, the total charge of the electrons that screen the impurity must be equal to the ionization state, big Z, of the impurity, 1 in our case, in all practical cases. The Thomas Fermi-Debye-Huckel screening violate this condition. It's called Friedel's sum rule. Essentially, it's a sum rule regarding the phase shifts. It tells you what the sum of all phase shifts of all angular momentum have to be. This has been studied in addition by the work that Bennett and Loney did by Meyer and Bartley, again, a little bit earlier, and they have actually shown what are the corrections that you can have to, say, the Brooks-Haring scattering rate caused by these phase shift corrections. And you can distinguish between attractive and repulsive interactions this way. This will come in handy when we'll deal with interparticle interactions, electron-electron holes. Beside the fact that in one case you have electron-electron, you have undistinguishable particles, and instead for electron holes you have distinguishable particles. But also the scattering potential will be corrected by these phase shift corrections. That can explain some of the experimental information that we have from the minority and majority carrier mobility. Another issue that I discussed is the coherence between scattering with impurity 1 and then scattering with the next impurity. The fact that in the next impurity you have the incident wave which is interfering with the wave which has been scattered by the first impurity. So this can give you some effect. In low doping situations, especially at high temperature, typically you can say that this coherence will be lost because the wave which is scattered by the first impurity will probably be decohered by other scattering processes like electron phonon. But in high doping, this may be quite important. There is a paper by Amor, which dates back to 1967, in which he considered this effect. Hans Kosina in Vienna has done more recently some estimate about multiple. Typically multiple means only pair because it's very, very difficult to deal with many pairs, with many purities. But they've done some correction, and indeed there are some small corrections that you have that increase at heavy doping. At heavy doping, though, it's very hard to tell whether the improvement or the changes of the better model, so to speak, are really due to the accuracy of the model or not, because there are so many other issues that it's hard to deconvolve all the various effects. So I hope that I give you an idea about how complicated these issues are. Scattering with ionized impurities can involve many aspects. Some of them, it might be my fault, but I couldn't find any paper. For example, that distortion of the lattice, the central set corrections have not received much attention, and it would be interesting to see what happens. Again, this may matter in some situations and may be negligible in others. So the typical models that we will be dealing with also in the future are the Cornwall-Weisskopf and the Brooks-Haring model. Again, the Brooks-Haring gives you a scattering rate, which I list here, which is proportional to the density of states via the effective mass, proportional, of course, to the density of the impurities, and has an energy dependence which at large energy decreases with the square root of the energy. So hot electrons do not feel the effect of impurity as much as cold electrons or near equilibrium. Okay. Any questions about this general discussion? No? Please feel free to interrupt me anytime. This was complicated. This next topic is even worse, even more complicated. So basically, let me give a slide that I prepared trying to, oops, sorry, my clock. Let's wait for it to ring the hour. 10 of them. Okay, Coulomb interactions. Let's consider the simple case, which is already complicated, of a uniform electron gas. So let's ignore for now block waves and consider the electrons as plane waves. So the Hamiltonian can be written as the density of electrons at position r prime times the density of electrons at position r, and multiplied by the interaction potential between r prime and r, and then you integrate over the entire volume. In second quantized form, the density can be written as the Hermitian conjugate of the Schrödinger field times the Schrödinger field itself at position r prime, and the same for the Schrödinger field at position r. If we plug plane waves for this expression with Fourier coefficients CQ or CK for each Fourier components of the Schrödinger field, even in a solid, you may view this as creation annihilation operators of block waves in this case. Then what we have is a very simple expression similar to what we had for the electron-phonon interaction, if you want, that I discussed in higher order, second order process for superconductivity, except that now we don't have phonons, we have a Coulomb center. So we have an electron K and with momentum K, an electron with momentum, by the way, crystal momentum will be a little bit sloppy in my terminology here, which are annihilated by these two terms, and they're converted into a new electron with crystal momentum K plus Q, and another which crystal momentum, oops, this will be a minus, my mistake, crystal momentum P minus Q. So the total momentum is conserved. And the scattering strength of the vertex, as some high energy physicists would call it, is given by the Fourier component of the Coulomb potential. Okay. Now, if you want to deal with this, we have to ask a question. Are we dealing with it? Some part of this interaction, at least some part, already. We're dealing with a band structure in which we have used the Hartree-Fock approximation. In simulating a semiconductor device in which we have free carriers, we usually solve self-consistently the transport equations and drift diffusion with a Poisson equation. So Poisson equation, in some sense, already accounts for electron-electron interaction in some form. So what are we doing exactly here? What we're interested in is the following. Take this term, which is the C dagger K plus Q CK, and split it into two terms. Consider its average or its mean field component, which is an ensemble average of this quantity. I will be more precise in the future. I would have to deal with a density matrix here to define exactly what this little bracket means. But this is the average over all of the electrons that we have. It's related to the mean field approximation that we talked about in dealing with solving the spectrum of an atom in a Hartree-Fock approximation, and also dealing with the Hartree component in dealing with the band structure of a solid. So essentially we look at the average of this operator here. It will be easier to understand in a minute what this means, over the ensemble of all of the other electrons. So we split this guy into this term and whatever is left out, which is the guy itself minus this object. Okay, this is not strictly rigorously correct, but it gives the idea. So essentially what we're dealing with here is a bunch of electrons. The distribution of the electrons on average, time or spatial average, is given by this expression. So we take the average of these operators over this overall time and spatial average of the entire electrons, and we subtract it from whatever these operators are. So this will be the average. Whatever is left over will represent what we may call spatial and time fluctuations of the electron density, or average over the electron density. So near equilibrium, we say, well, the fluctuations are small. Let's ignore the fluctuations. So let's replace the product C dagger C plus CQ, K plus Q C, and this C dagger P minus Q P, CP. Let's replace it with their average, taken in this way. And let's consider only the long range component. Long range means bigger than a unit cell or bigger than the interelectronic distance. Typically, in simulating using the drift and diffusion approximation of your device, that's what you're doing. You're looking at the average over a long distance compared to the length scales that I just mentioned of your electron distribution. So let's ignore the Q over here and realize that this is just the Fourier component of the average electron density. This is the electron number, and this will be at the same thing. So it will be the interaction between the two densities at two different wave vectors, okay? So I forgot here V of Q. I should add the V of Q in here. My apologies. So this will be the Hamiltonian, which essentially is equivalent to the interaction between the density at one spot and the density in the other spot. Again, I forgot this V over here, okay, which will be a V of 0, the average potential. And this is essentially the Hartree component, the Hartree approximation that we dealt with. I added a Fock here because actually if these obey the canonical anti-commutation rules, we have Pauli principle already in place. So really this includes the effect of spin, so to speak, via the spin statistics theorem. So it's really what the Hartree-Fock approximation does. You replace this complicated electron Hamiltonian with the interaction between the density interaction, if you wish. Again, my apologies. I'll fix it before posting the slides and the updated slides on the class pages. Now, off equilibrium instead, we have to consider what happens to the fluctuation part, so to this term. So when we deal with electron-electron interaction here, I will mean specifically the interaction between free electrons or free holes or free electrons when we have a bipolar situation. And only I will limit myself to the fluctuating part. So whatever is the mean field that is due to the presence of the charge due to these electrons, that's already taken care of in a band structure calculation or in the calculation of the average long-range potential, which is essentially the potential configuration that we usually deal with in an electronic device. So this is, I hope it's clear. So what we're dealing with now is the fluctuations away from equilibrium. And this is what we mean by Coulomb interaction between the particles, two particles. Actually, I should say interactions among many particles. Now, this is a big problem. I think it has been solved, I think in the 1940s, for a homogeneous electron gas, not in solids, by Gell-Mann and Bruckner, using an extremely complicated Feynman diagrams technique. So I will not go there. I don't understand it myself. But in dealing with solids, the problem has been studied by what's known as the famous Pines-Bohm quartet of papers. It's not a musical instrument quartet. Bohm and his students, David Pines, both Davids, published a series of 4 papers. The first 3 actually are co-authored by Pines and Bohm with different orders of the authors, I think. Excuse me. The last one by Pines, who went on and studied effects in superconductivity, which is coming on around that time. And they showed mainly condensing these 4 thick and heavy and long physical review papers. They showed the following. You can split these electron-electron interaction, again, the fluctuating part, into a long range and a short range component. So in this sum over Q, you have a small q, it's the long range component, at short q, the short range component. The long range component actually, and that was a major discovery, actually happens via a new collective state of the system. The system collapses into a plasmon, which we saw before. So at long range, an electron interacts with fluctuations of the field, which are due to the electrostatic field or the electrostatic energy, which are due to the slight deviations of equilibrium of a homogeneous electron gas, which are plasmons. We discussed it before. We saw what they're due to. If you perturb a homogeneous electron gas, which is a gallium of negative charge embedded in a gallium of positive charge fixed, you move a little bit, you subtract, if you want, some density of electrons at one spot. This will create a hole where there will be some exposed positive charge. Then the electrons will try, or this gallium of negatively charged particles will try and move into the positive spot. It will overshoot it, as in a harmonic oscillation, and this will be plasma oscillations, which are small deviations of equilibrium, so the small fluctuating part. And short range instead, plasmons do not survive. The process that is responsible for the decay of plasma, or there's more than one. One is collisional damping. Plasmons can also interact with impurities, with phonons, and they can decay. Decay means they decay into electron hole pairs. And by the way, here by electron hole, I mean an electron removed from the Fermi C below the Fermi level, not a hole in the valence band of a semiconductor. But however, an intrinsic, most important process that happens in an ideal system is that electrons can surf plasmons. View plasmons as waves, charge waves, which are propagating in the material. And although we usually describe them as a fixed frequency, so dispersionless, because the derivative of the frequency with respect to wave vector vanishes. Actually, if you do calculations a little more accurately than the approximated description that I gave you before, they do have a little bit of a dispersion and they move with some velocity. So they're like acoustic-like behavior. the velocity is the slope of the omega versus q dependence. Electrons which have a phase velocity which is equal to the phase velocity of the plasma can literally surf them. A surfer takes a wave, rides a wave, and it subtracts energy from the wave. That's why it acquires, the surfer acquires kinetic energy. Similarly, electrons which have the same velocity of the wave can subtract energy from the plasma, and the plasma eventually is dissipated by this process. This is a process which is called Landau damping and results in the fact that plasmas decay very quickly into single particle excitations. And again, I mean, they take an electron out from the Fermi sea and they move it up above the Fermi sea, so leaving a hole, sometimes called a correlation hole, in the Fermi sea. So at short range, electrons do not interact with plasmas because these plasmas do not exist, or if you wish, they exist as virtual excitations that don't last long and they decay into these pairs. So really the interaction becomes a single particle or pairs interactions. Two electrons will see each other as single particles, and we can describe this as a Hamiltonian of single particle excitation and use, here things get tricky, but let's say the firstborn approximation, or maybe even corrections to the firstborn approximation, exactly we described in purity scattering. So this is in a nutshell what we did. This is our Hamiltonian. This is the Hamiltonian expressed in second quantized form. This is our scattering potential, the potential between the density, so to speak, at one position and the other. And we have to deal with this. So we will split the discussion into the short-range component, the electron-electron interaction at short range, and then the long-range component. Short-range component usually means within a screening length. Two electrons which are within a Thomas Fermi or the Biohucka screening length will interact at this short range, a single particle excitation. Beyond the screening length, instead, the interaction is via plasmons. So essentially you solve your Poisson equation, but then you also account for oscillations away from the result that the Poisson equation gives you, which is the mean field, grand mean field approximation, and you look at plasmons as elementary excitation above this equilibrium condition. This is a little bit of a discussion that I gave already, so I don't have to go through again. Notice, by the way, that sometimes, as in many cases, there is an issue. I should have mentioned it also when we're talking with the electron-phonon interaction. In many papers, you will find that the dagger usually has a subscript of the crystal momentum, which comes with a minus sign. It's a matter of convention. I usually assume that C sub p is the Fourier component of the Schrödinger field associated with e to the I p dot r. The C dagger is associated with the complex conjugate of that plane wave, e to the minus IPR. So some people put the minus in the P here. I usually don't, but it's a matter of notation. It's not a matter of substance. So again, view this interaction as an electron crystal momentum K and an electron crystal momentum P. They interact via Coulomb interaction, which is given by the usual expression that I had here for the vertex. By the way, the dielectric constant clearly is the dielectric constant calculated at very high frequency, at which the valence electrons respond. Those are assumed to respond, but conduction electrons do not. We call it epsilon infinity in this context. And then through this interaction, through this vertex, they exchange a momentum q. Again, my same problem that I had. I'll fix it when I'll post it. This is p minus q, or vice versa. 1 minus the other places. Okay, we're summing over q's anyway, so the sign, whether I plot it here or here, doesn't matter. Okay, so essentially, we go and look at a perturbation away from the Hartree approximation. Again, this is a discussion of what I told you already, and you can read it, but essentially it says that at long wavelengths, you have a plasmons, but plasmons at short wavelengths decay. This is in notation. Whenever the plasma frequency is equals to the difference that you may have between an electron that has the Fermi energy and it's moved to a Fermi energy plus Q. Whenever this happens, so whenever you can take an electron from the Fermi sea and move it above the Fermi level, then you have the possibility that that plasmons decay into electron hole pairs. So essentially, the plasmon, which is this wave which is propagating in your Fermi gas, excites an electron from below the Fermi level and moves it up, and the plasmon decays. And this gives you, essentially, depending on whether the Q is parallel or anti-parallel with Kf, you have a range of wave vectors Q of the plasmons in which this can occur. And this is shown in this picture, which is well known. So if this is the plasma frequency, this is the wave vector expressed in units of the Fermi wave vector, this is a zero temperature picture. So the plasma can persist as long as there's no possibility of exciting an electron from below the Fermi sea above the Fermi level, conserving energy and momentum. This cannot happen in this region. There is a region in which this can happen up to this point, which are the two limits of this equation, the plus and the minus, depending on what is the angle, 0 or pi, between Q and Kf in this isotropic limit, and then we re-enter the Landau, the plasma region. So this region is the single particle region. Typically, we never consider this region here because it's at Fermi levels, which are wave vectors which are very large. So essentially, we deal with plasmons at Q's or distances 1 over Q in this range, and then we go into the single particle region in which we consider single particle interactions. So let's look at short range interactions. Maybe it's a good time here to have a little break so we can reconvene. What time is it now? What is my atomic clock telling me? Okay, 10:19. We can meet at 25 after the hour, if it's okay with you, and start talking about the short-range electron-electron interaction. Good? Okay. Back online, everybody. Enjoy your break.
Yeah.
Okay. So, I put here lots of details. I don't intend to go through all of them during the lecture here. You can read them. They're kind of boring. I want to emphasize the physics that enters here. So if we use the, oh, by the way, you will recognize many of the assumptions that we made dealing with impurity scattering, with some, of course, some changes, which are mainly due to what happens to the matrix element for the Coulomb interaction, because we're dealing with undistinguishable particles. So if we use the first Born approximation to describe our interaction, the scattering rate for an electron in a particular band, nu, with crystal the momentum k at a position r, with another, has to be summed over all the possible scattering processes with all of the other electrons. So we have to deal with how many electrons do we have at the same position. At the same position really will mean within a screening length, and we'll talk a little bit more about it. We sum over the distribution function of all the, let's call them partner electrons, the electrons with momentum p, in this little diagram that I have here. By the way, I have fixed the signs that I have here. Okay, so we consider an electron of momentum k. We have to consider all possible interactions with all partner electrons p, which are nearby, so within a screening length. In this approximation, we take the distribution function at the position of the primary electrons. We sum over all possible final momenta, crystal momenta of the partner electrons, sorry, the initial of the partner electrons. And then we sum over all possible final states. We can either sum over the momentum transfer or over the final momenta of the primary electrons. They are connected by momentum conservation. Of course, we must have, if we are dealing with a degenerate system, we must have available states, so empty, and the final wave vector k prime in band nu prime. Similarly, available final states for the partner electrons, the final state of the partner electrons. So these are factors that we can simplify and just use one for both of these terms if we're dealing with a non-degenerate system, since f would be very small. And then we have energy conservation, in addition to momentum conservation, which will come, it's included in this matrix element. This is a very messy thing to deal with because it's a two-body collision. So far we've seen electrons scattering with phonons. It was a two-body, but so this is a four-body, strictly speaking. That was a two-body and electrons scattering with the phonons. Now we have two electronic states in initial condition and two electronic states as final conditions. So it's very complicated to deal with algebraically and also numerically. Okay. So the assumptions that were made is, first of all, we're considering that we have momentum conservation. I should add here a G vector in principle. Remember that if we're dealing with electrons which are described by block states in a crystal, crystal momentum is always conserved up to a wave vector of the reciprocal lattice. We have assumed that all electrons contribute equally, so we're looking at just selecting a partner electron out of a distribution of electrons that we must know. So if we want to deal with a simulation of a device, this is a major issue. It renders the transport equation highly nonlinear. Actually, that was the original formulation of the Boltzmann equation, because we have to deal with a distribution of partner electrons. And since we have to, our problem is to find out what this distribution function is, this requires iterations. So it's a nonlinear problem. The distribution function, we will talk more when we deal with the Boltzmann equation. I'll assume here it's normalized to the total density this way. Sometimes this is normalized to 1 or 2 if you include the spin. But we'll assume that summing over all possible crystal momentum of all electrons and summing over all the bands just gives me the total electron density at position r at time t. Okay. Again, the g's, which I have not considered here, that I should assume here, are reciprocal states, vectors of a reciprocal lattice. Before showing some results, notice that we have to deal with lots of complications that we have discussed already dealing with electron impurity scattering. This expression is the first Born approximation. This matrix element will be between unperturbed wave functions, block waves, initial and final. So we'll have 4 block waves, the 2 initial block waves, K and P, and the 2 final block waves, K prime and P prime, in their respective bands. In principle, we would have to go beyond that. In the case of impurity scattering, we saw that the first Born approximation fails to distinguish between an electron scattering with an acceptor or a donor. It treats them equally. But we saw that there are some corrections that people can use. I'll show you some results. The same here. We may have to have phase shift corrections. Typically, what one can do is go to the center of mass, and then it becomes similar, expressing formally, similar to what we saw for the electron impurity scattering, except that the electron mass now will be the reduced effective mass. We would have to deal with these things. I didn't mention about them with the electron impurity scattering, but in principle, the matrix element will also have to account for the overlap between the final state and the initial state, the wave functions in and out. These are simply one if we're dealing with free electrons. In a crystal, we have this nuisance. We already saw that it enters on all scattering processes that we're dealing with, even electron-phonon interaction. So the matrix element will be the usual matrix element, the Coulomb matrix element. We'll assume that it is screened. So here we'll have just the Q squared plus beta squared. There should be a parenthesis here that I forgot. Okay. Okay. If we plug it in here, there is a little space here, so that saves me. Now the screening parameter and the general matrix element is a little bit different here. In electron impurity scattering, we have 2 distinguishable particles. So it's just a Coulomb matrix element, that's it. In this process, the role of K prime and P prime can be swapped. In other words, if we go back to this, here I'm depicting with the red color 1 electron with a blue color the other electrons. But clearly, the electrons are not distinguishable particles. So I can swap the 2. I can really say that the electron K goes to K plus Q or to P minus Q. So the final state K prime can be switched, can be swapped to the final state P prime. What is the difference? It's actually quite important. I'll give you an example where it may matter. The exchange, the energy, which is gained or lost by 1 electron and is lost or gained by the other, can be small or big. Maybe I can show you a plot immediately. Let me show the plot here. This is a particular case that I have in mind. Consider a MOSFET. This is the potential of the MOSFET, this is the source, this is the drain, and I have a short MOSFET and electrons travel almost ballistically. I drew this line as a diagonal line, meaning they can lose some energy to phonon swing. Okay. Now, this hot electron, once it enters the drain, can interact with the Fermi gas of the electrons in the drain. So we have an electron with a high energy that can interact with an electron with a low energy. You have 2 possible ways of looking at the problem. One, this electron loses a little bit of an energy. This is a small amount, could have made it smaller yet. And the same energy is gained by the other electron. Of course, energy is conserved in time. The total energy is conserved in the process. In this case, the energy exchange by 1 electron, or gain or loss by 1 electron, is small. So it is a small frequency associated with this process, which means that the screening, the dielectric screening that we have, has a small omega in the denominator, if you remember the expression for screening. So essentially, it's a static process. This electron interacts with this guy, and the Coulomb interaction is screened statically. However, let's call this a direct process. However, there is an exchange process. By the way, these two names are arbitrary. I can swap them, okay, since particles are not distinguishable. I can view this electron as going to this state, and this electron going to this state. Now the energy, which is gained or lost, so exchanged among the two electrons in the process, is very large, which means that the frequency, if we want to expand into Fourier components this process, the frequency is large. So the process is screened dynamically. If this frequency is bigger than the plasma frequency of this gas, then the interaction is essentially unscreened. This results in a very strong Coulomb interaction that you wouldn't expect because of the high density of electrons that you have here. This is typically the result of this, of the fact that the electrons are not distinguishable. If you want, it's an exchange process that causes this issue. For example, if this is an electron that has, say, 0.7 electron volts, this guy might be an electron with 0.1. So we have a 0.6 electron volt difference between these two. So the energy that the electron can lose here can be very tiny, but if we in the direct process, but in the exchange process, the energy that we have here can be 0.5, 0.6 electron volts, which is much bigger than the plasma frequency that we have here. Even if we have, say, 10 to the 21st doping, the plasma frequency will be, I forget the exact number, less than 200 electron volts. So the exchange energy can be some 3-4 times bigger, well, 2-3 times bigger than the energy, than the plasma frequency. And so this interaction is essentially unscreened, or one component of the interaction is unscreened. So we really have to be very careful in considering the fact that the matrix element that we have is actually resulting from the contribution of the direct process in which this frequency is small, is whatever it is, but it is small, and the other process in which now we have swapped K prime with P prime, so we have exchanged or swapped the final states of the two electrons, and now the frequency involved in the process is very high, can be very high, whatever it is. So again, this is arbitrary, what I call exchange and direct. How do I do that? Where do I get the total matrix element? Well, I do it from assuming, and this is where it gets a little tricky, whether the wave function of the two electrons, the initial two electron wave functions, and the final two electron wave functions are symmetric or antisymmetric. This depends on the spin state of the system. You remember that two electrons can be either in a triplet or in a singlet spin state. If the two spins are parallel, then the total spin angular momentum of the two electrons is 1. So you can have 3 possible states with the z component of the total spin angular momentum being 1, 0, or -1. This is a wave function which is symmetric in spin state, in a spin variable, so it has to be antisymmetric in the coordinate, in real space coordinates, the real space part of the wave function. You remember that we discussed at length what is the effect of the exchange energy. In this case, the matrix element will have some expression because the wave function is antisymmetrized, so the electrons tend to be farther away from each other. On the contrary, if the electron is in a singlet spin state, then the spin wave function is already antisymmetric, so the spatial component of the two electron wave function has to be symmetric. Therefore, they behave like bosons. They are closer together, and interaction is stronger. So what you have to do is you consider the full square matrix element as given by 1/4 of the spin singlet component and 3/4 of the spin triplet components. And if you do the algebra, you get these plus and minus signs for the two, which are the results of the plus or minus that you have in the symmetrized plus or anti-symmetrized minus two-particle wave function. And you do a little bit of algebra and you find this expression. So essentially you have a direct and an exchange components, and then you have something which is, you may view it as an interference or the exchange term between the two processes. So the effect is not academic, because as I showed you in that example, in one case you may have, say, the direct component, which is strongly screened, very weak, but you also have the exchange component, depending on how you name it, which can be very weakly screened and so extremely strong. And that may result in a very fast thermalization of the electrons in a drain that you would not expect if you didn't account for the fact that that the wave function has to be symmetrized or anti-symmetrized. I had a discussion with Carl Hess about it years ago. I'll show you some effects, okay? First of all, the importance of some things, some effect. This is the screening parameter, the square screening parameter, with respect to the Debye-Hückel screening parameter that you have in a non-degenerate situation. So I'm assuming a density of 10 to the 18 electrons per cubic centimeter. And you see that screening gets weaker if you consider dynamic screening. Okay. Here I'm plotting it as a function of exchange momentum, and I'm using a frequency which is equal to the parabolic expression that you have for the momentum which is exchanged. Weaker screening in this range means a stronger interaction. So the effect is significant. If you look here, it can be a very big effect in terms of what is the difference between static and dynamic screening. So what will be the strength of the statically screening, what we call the direct process, and what will be the strength of the what we call the exchange process. Again, the names are arbitrary. Phase shift corrections. So we saw for impurities, the first-born approximation does not distinguish between donors and acceptors or attractive and repulsive interactions. Same thing here. The classical statistics is, this is the scattering rate as a function of relative energies between the two particles in the case in which we have simple first-born approximation. This is what we have in case in which we consider the symmetrization and anti-symmetrization. So the matrix element assuming both the exchange and the direct process. So that's the first thing. And these are the difference, look how big they are, between attractive and repulsive interaction. For attractive interaction, which is electron hole, for example, that makes a big difference because the wave functions tend to be closer together. For electron-electron interaction instead, which is a repulsive interaction, you see that it is much weaker. So these are not simple or weak effects. They're not simple to deal with, of course. The results, by the way, have been obtained by using simply the corrections that have been suggested empirically. So they tabulated the ratio between the conventional way to calculate the scattering rate and the scattering rate obtained from the very complicated phase shift analysis that they did. And I've simply multiplied the anti-symmetrized or symmetrized matrix element, this by the correction that was reported in the paper that I cited before. So these are big effects. They're extremely important, okay? This is interparticle scattering rate, okay, using again various approximation. In one case is with the Debye-Hückel, and this is not a big effect actually. The screening parameter that I cited here, notice that I have a dependence of Q and omega. This is, you have to cook it up somehow by looking at the expressions that we saw before. You remember that in dealing with screening, we looked at various limits. I told you that in a limit of long wavelength or small frequencies, so small q or small omega, you can find some expression that depends on only on q and omega. The general expression, assuming both q and omega, can be obtained if you remember the complicated algebra that I got from the Fetter and Waleka's book, in which you can do the integration analytically using the plasma dispersion function in the non-degenerate limit. in a degenerate limit, you cannot do it analytically. You have to do it numerically, and it's quite painful. So that's why I plot these results, as I plotted also here, in a non-degenerate limit, because I could use, I wouldn't call it analytically, but at least a closed form expression for the screening parameter. So it's a sad situation because electron-electron interaction can be quite important. There's been a belief of mine that is actually extremely important, and is actually what may prevent ever seeing purely ballistic transport. Whatever device you have, you're going to have contacts. In contacts, you have a high density of electrons, long-range interactions, so plasma-mediated long-range interaction are going to be effective no matter what. The shorter the device will be, the more you expect ballistic transport, but the less you will see really transport occurring without any collision at all. If you call electron-electron interaction as a non-energy dissipative process, then you may call it ballistic, even if there is a strong electron-electron interaction, but the effect on the distribution function can be quite important. So I hope I've given you an idea about the complications that you deal with. How do we deal with in simulations? For example, how do you deal with the various factors 1 minus f that we had to look for the presence of available empty final states for the electrons p and k? Sometimes you simply use the equilibrium distribution function calculated given the local temperature and density that you have in your simulated region. Doing it self-consistently is a little tricky because, again, this is your unknown, so it makes the problem non-linear. This is a big issue. There have been several attempts, particularly in the Monte Carlo community, how to deal with it. Gathering the statistics as accurately as you need for a mesh in k-space and in real space, it's almost impossible because you have too many bins in your phase space in which you have to gather statistics whether you have electrons in that bin or not, and it gets really complicated. Screening sometimes is dealt with a simplified approximation, ignoring the energy dependence, considering, for example, unscreened interaction for the exchange term, because the frequency when the energy exchange is very large, typically when, as I said, when the frequency is much higher than the plasma frequency, you can ignore screening and using instead the bihucal of Thomas Fermi screening for the director. So you have to essentially use your intuition and circumvent all of the serious problems that you have. I've shown lots of plots about results that I got from Monte Carlo simulations of electron transport in various fields. What is the electron phonon scattering rate on the average? This is average over the initial and final distribution function by Monte Carlo sampling using various conditions, and you see how dynamic screening or static screening can change things quite dramatically. For phase shift and dynamic screening, the interaction can be quite strong compared to the static screening and non-phase shift because of the effect of the weak screening that affects what we call the exchange process. Okay. A simple case that you can find in the literature is parabolic bands. This is simple. Then you can do things more or less analytically. So our equation now can be simplified. You can make many simplifications due to the fact that you know the density of states, you know everything, and you replace the distribution function with just the density, and then just an interband process, and you pick an electron with a particular wave vector. So this is the scattering rate between two electrons, one in band nu and the crystal momentum k, the other in band nu and crystal momentum p. We're assuming that you have a density n of r, maybe if you're a time-dependent simulation, the same time t, and you can find that the expression is a little simpler, doesn't look that simpler, and you can use these various screening parameters, as I said, with some approximations evaluated at the exchange or direct momentum and energy transfer. These are the what we call before the direct matrix element, the exchange matrix element, and this is the interference term between the two. Notice that it leads to a, like all exchange process, it leads to a depression of the scattering rate. Okay, these are some expressions that we can use in terms of the plasma dispersion function. These are details that, of course, I will not ask in during the exams. These are really tricky details. Typically, one ignores intervalley processes because of the dependence on the difference between initial and final wave vectors. If in an intervalley process, these terms will be big. So you can go to the center of mass frame. You define a center of mass initial wave vector and final wave vector. You do a little bit of algebra. Energy conservation can be written in simple ways by looking at the relative initial and final wave vectors. Rather amazing that one can deal with this simplification. I'm assuming that the bands are spherical, so isotropic, and parabolic with an effective mass m star. Then we get something which is very similar to the expression that we had for scattering with impurities. It's essentially identical. And so you find exactly the same expression for the direct and exchange, direct term. For the exchange and interference terms, you get this more complicated expression. If you have time, if you feel like it, it would be a good idea to go through the algebra to see how to perform this integration. It's not terribly difficult. Can be done analytically thanks to the simplifications that we have. And this is interesting for one reason. This is for electron-electron interaction. By the way, you can find in Ridley's book an expression which is very similar. In the case of distinguishable particles, so for example, I wrote here electron-electron, maybe electron-hole, although here we have to assume that the holes are the same effective mass of electrons. So let's assume classical electrons, which can be distinguished. Then we have an expression which is very similar to what we found for the electron impurity scatter. It's the same, except that we are in the reduced center of mass frame. So this k vector now is relative k vector that the two electrons had before an initial state. You see the same energy dependence that you have on the relative energy of the two electrons, and there will be some factors of 2 and 4 here floating around because really this should be the reduced effective mass. You can find some limits, for example, in the limit in which you have very relatively small energies. In this case, you approach the semi-classical result. That's because at small energies, the electrons are far away. Okay, so these are things that you will find, expressions you will find in the literature, very commonly used. They are important. Notice, for example, that even with this simplified case of interaction between electrons in spherical parabolic bands, the corrections due to the fact that the electrons are indistinguishable particles is quite important, can be quite important. And I showed in a few plots how things can change significantly. This particular case is the most dramatic one. It's probably the strongest I've ever seen. What I show here is also what is the emission rate as a function of the energy which is lost by this red electron. If you account for regular Thomas Fermi screening without accounting for this dynamic effect that make a very different, make the exchange and the direct terms play a very different role, you see what you get. If you look at a short-range interaction only, which means we look only at components which are for Q, which is bigger than the screening length, and this is instead accounting for the full expression you may get, and you see that you get a peak at the plasma frequency. So this is a plasma-mediated interaction. So what this is using the full, let's go back here, the general glorious expression that we have here, using the full expression for the screening parameter due to the random phase approximation. This will give you automatically the separation that Pines and Bohm gives about the long range and short range component. So this accounts also for interaction with plasmons. And you see that you have a peak compared to the short range only is extremely large. So this is a plasmon-mediated process in which electrons emit the plasmon is Landau damped and decays into an electron-hole pair. And you see this peak. The effect is, you say, what do you care? Well, it expresses the relaxation of this distribution function. Of course, the average energy of the system will not change. You simply move the energy from the hot electrons to the cold electrons, and you end heating up the drain contact. It's what I think is called the Peltier effect in thermodynamics, in which hot electrons can heat a distribution of cold electrons. But the important thing is that if you look at the distribution function that you have as you enter the drain that you get, you can find that with or without Coulomb interaction, the effect is very different. Without Coulomb interaction, you have a distribution function which is hotter, clearly, because the electric field has accelerated the electrons along the channel. And then there is this, this is a detail which, however, has kept people busy for years, especially Monte Carlo people, busy for years. It was noticed first by Peter Price many years ago. If you look at electrons which are traveling over a finite distance in a given field, of course you would see a distribution function which is hotter, clearly does not decay with the KT over here. But then when you reach the point at which the electrons have reached the applied bias, in this case 1 electron volt in this 0.95 actually, in this particular thing. From then on, the distribution function has a decay, which is the room temperature decay. Clearly, it's related to the equilibrium distribution function that we're assuming. But the exact details of why this is so remains a little bit of a mystery. I mean, you find it in Monte Carlo simulations, everybody does. But why it is so in elegant, simple physics terms, boy, my clock, I am knowing clock. It's a little bit of a mystery. I had long chats with Peter Price about this. I think unfortunately passed away a few years ago. However, if you look at Coulomb interaction, the main effect of Coulomb interaction is trying to get this as a straight line, essentially thermalizing the entire distribution function at clearly the temperature, which is a higher temperature given by the average energy of the system. So what the Coulomb interactions do, particularly the strong Coulomb interaction due to this exchange term, they remove electrons at low energy and they place them at high energy, but by shifting so they increase, if you want this, but you notice there is an intermediate region in which the number of electrons is smaller. So the average energy is preserved, is maintained, but you have a higher energy component over here. And this can lead to interesting details that people are worried about. One typical issue that is due to this effect is how come that people dealing with silicon on insulator field effect transistors were seeing impact ionization at a drain bias which was way less than the band gap of silicon. You expect impact ionization to occur, we'll talk more, at the band gap, of course, actually higher because of momentum and energy conservation. But at the minimum, the absolute minimum, you expect, even if ignoring momentum conservation, and I'll tell you why there is a reason to do so in some materials, you would expect no impact ionization to occur at 1 volt. An electron can be degenerate in the source, has an energy around 1/10 of an electron volts. By the time it gets to the drain, it will have the VDS, the applied VDS, 1 volt plus the initial energy, 1.1, and can impact ionize. Instead, people were measuring the pileup of holes. We shift the threshold in SOI FETs, even at, I believe it was as low at 0.7 EV or VDS. And this is caused by this effect, by the fact that the strong Coulomb interaction can actually result in a tail of electrons that extends way above the maximum kinetic energy that you expect, which is 0.95 eV in this case. So it's an interesting effect, and it's due to the electron-electron interaction. Okay, this is regarding, at least except for this figure, where I use the full RPA expression for the screening parameter, which accounts for long-range interaction as well. And since it was a full RPA calculation, it also accounted for Landau damping automatically. But now we move to purely long-range interactions. So short-range interaction can result mainly in the thermalization of the electron distribution, an attempt to thermalize it. Whether they manage to thermalize it or not depends on time and distance and space that the electron-electron interaction has to work with the distribution function. But it's a thermalization, and there are some, if you want little details, the current is not the main current, the drain current in this device is not affected much by these effects. Long-range interaction have a different flavor. So in general, you don't expect to see a current resulting from scattering with plasmons with a long-range interaction. I think I mentioned it before. When an electron excites a plasmon, it loses momentum, but the momentum is just given to the plasmon, so to the collectivity of all of the other electrons in the gas. So you don't lose momentum. There might be second-order effects. The electron distribution function may be modified because of the electron that loses momentum and energy to a plasmon. It redistributes the energy and momentum to all of the other electrons, so the electron energy distribution function will change. Moreover, plasmons themselves can be collisionally damped, can also scatter with phonons, with defects, with impurities. And so if this happens before the plasmon can decay into an electron-hole pair, so a single particle excitation, and can be damped by these collisional processes. So momentum will be, and energy will be effectively lost by the electron in an electron-plasmon interaction. This is sometimes the case, particularly in heavy doping materials. In bipolar transistor, the situation may be different. For example, a minority electron interacting with the whole plasma in the base of an NPN bipolar transistor can exchange momentum with the whole plasma, and these holes can leave through the base contact before decaying back into electron hole pairs in the base. So that can result in a net loss of momentum, and so it affects directly the mobility of electrons in the base of bipolar transistors. I guess talking about BJTs shows my age. We're not used to those anymore. They're not used much, except some power applications, of course, but in VLSI, they're not used at all. Anyway, one can say, okay, what is the scattering rate between electrons and plasma? How do I calculate it? You remember that we were dealing with the Furlich interaction. I told you the scattering potential you get with a Furlich interaction is exactly what you get when you calculate the scattering potential due to plasmons. You remember those calculations that we did of the potential associated to one plasmon, except that dealing with the Furlich interaction, you wanted to isolate the component of the dielectric response due to the longitudinal optical phonon only. So we introduced this dielectric constant and calculated the scattering rate. For plasma, you get exactly the same expression, identical, except that this Furlich factor is now replaced by 1 over the epsilon infinity, if you want, the valence band dielectric response. And this was calculated, for example, by Paolo Luri and Dave Ferri some years ago. Boy, we're getting old, 1985. Okay. We have discussed also the case in which electrons can scatter with coupled longitudinal optical phonons, plasmon modes in doped polar semiconductors. I showed you what Ridley Ridley's treatment of the process is, or interfaces, like at the interface between a dielectric SiO2 or whatever and a semiconductor. But except for this, scattering with plasmon per se is not a major component. I will not go into the details about what happens when an electron in a channel scattered with plasmons in the source, for example, or plasmons in the gate of a material, where momentum can really effectively be lost and can be a direct effect on the drain current. This is a rather complicated issue. I will not mention it, but please feel free to ask, and I can try and answer it as best as I can from what I recall. Instead, one of the major issues of long-range interaction, and this is another wasp nest that has been discussed in the literature for decades, is bandgap narrowing. So bandgap narrowing is an effect which is seen experimentally when you doped a semiconductor to high levels. You see that the bandgap, as measured somehow, and I will have to specify what somehow means, the bandgap shrinks. And there are many causes of this effect. The bandgap can be measured in two ways. Optically, you can look at the shift of the absorption threshold in the absorption spectrum, optical absorption spectrum, optical or infrared, whatever it is for a given material. You can measure it electrically. For example, this used to be a big issue. Again, I'm coming back to bipolar junction transistors. In BJTs, the base current can be, of course, it's controlled by, so not the base current, but the electron current, the collector current, is controlled by how many electrons can be thermoionically excited over the emitter-base junction barriers. And depending on what the bandgap in the base and in the emitter is, this barrier is clearly different. And if the emitter clearly is heavily doped, the bases have been also very heavily doped in the end of the life cycle of bipolar transistors in logic applications. And clearly, so you have to be very careful about how the bandgap changes when you increase the doping. There are several issues. The main one is, of course, if you have many impurities, they can create an impurity band. We'll talk a little bit more later. And that's not related to Coulomb interactions per se. If you start squeezing too many arsenic atoms or boron or phosphorus atoms, approaching the solubility limit, so before they begin to cluster into lumps, when you reach and exceed the solubility limit, they begin to be close enough so that electrons essentially can be connected via tunneling from one impurity state to the next. And then you create an impurity band, you distort the density of states, the bottom of the conduction band or the top of the valence band begin to be broadened or smeared out by a tail, sometimes called the Urbach tail, of the disorder, which is induced by the random diffusion, the random configuration of the impurities, and the tunneling of electrons from one impurity site to the next, forming a band. But there are also issues which are related to Coulomb interaction per se. I would follow here a treatment given by the paper by Jerry Mahan that I mentioned before. It's a wonderful paper, by the way. So the idea is, if we have a material, a dielectric, so a semiconductor in particular, which has a large density of free carriers, what we can have is several Coulomb interactions. So here I depict in a solid line the bandgap of my ideal semiconductor. Silicon, room temperature 1.11 or whatever it is, your favorite number for the bandgap of silicon, 300 Kelvin. But then you begin to have electrons or negative charges in a conduction band and some positive charges in a material. Here I draw it in a valence band. This could be dopants, so they give a positive charge, And these are the electrons, say in an N-type silicon, phosphorus doped. So here you have donors, here we have electrons, and there are several interactions between these charges. You can have a Coulomb repulsion among the electrons in a conduction band. This will increase the energy of the system. There will be a Coulomb repulsion of, if you have p-type silicon holes. If you have dopants, you may think about a Coulomb repulsion between the dopants that will increase also the total energy of the system. But there will be also a Coulomb attraction between the negative and positive charges. For example, electrons and the dopants that you've introduced. This will result in a change of the gap. So Mahan used a simplified version of the model, which I think he called the modified Hartree model. Again, same paper. The idealized scenario now is the following. Let's stick to silicon. Let's place some dopants in silicon, and let's assume that these dopants are distributed very regularly in a cubic lattice. It won't matter too much. And let's assume that the electrons are just a gallium of negative charge, so a continuum of negative charge, fairly high density. So rather than a little dot here, I represented it as a blob, but this could be a continuum of red stuff, negative charge that you have in a conduction band. The valence band is kept fixed by definition because there's nothing that goes on with the dopants. They're fixed there, they stay there. So the change in the gap will be given by the change of the Fermi energy that the electron gas will have. If we increase somehow the kinetic energy of these electrons due to the Coulomb repulsion among the electrons, the interaction attractive between the electrons and the dopants, if we increase this kinetic energy, this potential energy will also increase the kinetic energy by the virial theorem. But since the density of the electron has to be the same at equilibrium according to the Fermi-Dirac distribution, an increase of the kinetic energy has to be compensated by change in the Fermi level, and so the shift of the conduction band that you have. And this will be how we calculate the band gap narrowing. So in this model, the narrowing of the band gap is happening totally in the conduction band. Nothing much happens in the valence band. This is a simplified model, but it agrees quite well with the experiments. So what we do is we consider this simplified model. The dopants are frozen in a cubic lattice. We calculate the potential energy of the gas, the total potential energy, or the total energy if you wish, by looking at the total kinetic energy due to the Fermi energy. Let's call it kinetic energy. So the average energy of the Fermi gas. We consider the Coulomb repulsion among all of the electrons. We consider the attractive Coulomb interaction between the electrons and the gallium. Having calculated this total energy, the kinetic energy, and the potential energy due to these Coulomb interactions, we will calculate the kinetic energy changed, how much it changes, by using the virial theorem. These are 1/r forces, 1/r² forces, 1/r potentials. So we can use the virial theorem to calculate the time average change in kinetic energy due to the potential energy that we calculated here. Having calculated this change in the kinetic energy, since the electron have to be described by the Fermi-Dirac distribution, a change in the chemical potential has to be compensated by a change in the shift of the conduction band. And this will be our band gap narrowing. So this is the strategy that Mahan followed, and I will outline it before. I don't think I need to go through this calculation before. This is just the kinetic energy due to the Fermi degeneracy of the system. You just calculate the average energy, average over the Fermi-Dirac distribution function, and define what it is. And you can calculate it relatively simple. The Coulomb at the change of the potential energy calculated per dopant due to the electron donor interaction is negative because it's an attractive interaction. You can calculate it by considering the volume of a dopant, again in this cubic lattice, but we'll assume that each impurity occupies a volume which is a spherical volume or radius R0, which is inversely proportional to the cubic density, the cubic root of the density of the dopants that you have. We're assuming a charge neutral material, so this would also be equal to the electron density. And you can simply calculate which is the change, the interaction energy over this volume, which is a negative interaction energy. This is just 1 over r, the interaction, the Coulomb potential multiplied by the r square that you get from the going to integration from Cartesian coordinates to spherical coordinates. And you get some number. I defined with kappa this particular value here, whatever is the prefactor in front here. This is about 2.5, so it's minus 2.5, and then there is this e squared over 4 pi epsilon infinity of silicon. It is about, I call it kappa. This depends on the average distance between the electrons and the dopants, which is proportional to the cubic root of the density, or the inverse of the cubic root of the density. You can calculate the repulsion among the electrons in a similar way, except that now we're using the charge density of the electrons in this gallium per unit volume, and you do the calculation and you find something similar with a prefactor that rather than having a 3/2 as a 5/3, but then it's the same thing. It's about 1. Okay, and it's positive because it's a Coulomb repulsion between the electrons. So the net energy that the electrons gain, or the change in potential energy, is negative and will be about 1.5, minus 1.5. Notice that the mutual interaction between the donors, this stuff here, vanishes because we're assuming that the donors are ideally screened, perfectly screened. So the total change in the Coulomb energy of the system will be, as I said, about minus 1.5. This is number, actually, you can mess it around a little bit. We're doing a little bit strange thing. We're assuming that the impurities are in a cubic lattice, but we assume a spherical volume occupied by each impurity. You can do better calculations. It's essentially something that you do when you calculate the Madelung energy of a crystal, depending on whether you're what particular close-pack configuration, hexagonal, cubic, or whatever you use for the impurities. They're all roughly 1.5, 1.4, 1.5, so not much. If you use the Bi-Huckel screening, then there is a little bit of a correction to the donor-donor interaction, and it's been reported that something similar to that is a 3/4 rather than times beta screening rather than what we have. But we'll stick with this expression over here. Okay. Now, this is the change in the potential energy of the system. What is the change in the kinetic energy of the system? Well, again, we can use the virial theorem. I hope that you remember what it is. It is a theorem that for a force of the type 1 over r alpha, to the power alpha, connects the time average kinetic energy and potential energy, so total energy of the system, time average over a big time, okay? And for 1 over r squared forces, one can calculate the change in kinetic energy from the change in the potential energy via this relationship. This 1 over 1/2, it's what happens for the Coulomb force, 1 over r squared forces. So Coulomb forces, gravitational forces, and so on. So by this, you can find that the change on the kinetic energy by taking these expressions over here is equal to essentially, oops, where am I? The opposite of this, okay? This expression. This is the change in kinetic energy. Now, what is the change on the chemical potential? Let's call it Fermi level, although we're dealing with interacting particles and the two things are not the same, but let's call it chemical potential due to this change in energy. Well, there is a relation in statistical mechanics that says that the chemical potential is due to the can be calculated from the Helmholtz free energy, the derivative of Helmholtz free energy with respect to the density, keeping the volume constant. This is a little tricky here. The Helmholtz free energy is just the total energy minus the temperature times the entropy. In our case, this results in a change on the chemical potential, which is given by the derivative of this guy, the total Coulomb energy that we have, on the density, but keeping the volume constant. And this is a tricky thing, okay? So we have to keep the volume constant, which means that we will express n as the number of particles times the volume. We take the derivative only to the number of particles and then insert the volume back then. So it is this expression. And it comes out to be this, about a third of what we had because of the cubic root that we have over here, okay? So this is the change in the chemical potential, and this results in a shift, is equivalent to a shift of the conduction band in order to keep the density constant, clearly. We want to keep the fixed density. This is the results of Mahan calculations in a dashed line over here. This is the band gap. It's a narrowing, there is a minus sign, so these numbers tell you how much the band gap in silicon shrinks as a function of density. You see the cubic root dependence. Here you have the optical gap and the electrical gap. They are different. And the reason is illustrated in this figure, which also will let me introduce another thing related to the calculations that are shown here, done with the semi-classical Monte Carlo calculation. The optical gap is essentially the minimum gap that you can see. Sorry, the electronic gap. The optical gap is some sort of an average direct gap. What I show here is in the x-axis should be viewed as position. These are the fluctuations of the potential due to the random fluctuations of the electron density and impurity distribution. Time average of it, so it will be the impurity distributions. And the electron density also fluctuates as well. So the valence band and the conduction band will fluctuate differently. The electronic gap that you see, for example, by looking at the barrier between the emitter and the base of a transistor, essentially has an onset for the thermionic injection over this barrier, which is given by the minimum gap that you have, the minimum barrier height. The optical gap instead measures something which is bigger. So the shrinkage of the gap will be lower when you measure the optical gap. It goes to zero here experimental. I don't remember what experimental data are from. But the electronic gap shows a quite good agreement with the model that Mahan did, except that we haven't talked about exchange and correlation corrections that are included in the calculation. I'll mention it briefly in the next slide. You can do this also by doing some Monte Carlo calculation. This is the fluctuations of the potential due to the fact that the electronic charge changes. If you're careful about using the correct number of particles, the correct mesh size, and so on, you can capture plasma fluctuations. And then what you have essentially is the smearing out of the edge of the conduction band due to these fluctuations, and in turn an increase in the kinetic energy of the electron locally, which corresponds to essentially a change in the Fermi, in a chemical potential. And you see that the semi-classical model that you can calculate is similar to what the model that I described before, the empirical model over here, which doesn't include exchange and correlation, gives you. So good agreement with experimental data. Exchange and correlation are a tricky business. Essentially what Mahan does, it goes back to the extremely complicated results by Gellman and Bruckner on the exchange and correlation energy of a quantum electron gas. By the way, notice that this is exactly the same type of expression that one uses in linear density, local density approximations for the Kohn and Sham density functional that you use for the calculation of the band structure in the LDA approximation. Okay. Details, I will not deal with it anymore. Any questions about this? So I think this is the major effect of the long-range Coulomb interactions. There are additional factors that I didn't talk about. These fluctuations, again, can result from the fluctuations on impurities, not only the electrons, and this is what causes the formation of the Urbach tail, of the impurity band that you have. in the absorption spectrum in heavily doped silicon, you see not only a shift on the absorption threshold, but also a broadening of the absorption spectrum. Ooh, come on. Okay. Any questions? Okay.
Max,
yes,
I have a question.
Yes, please.
Due to the tail of the conduction and valence band inside the gap, how can you define a sharp edge of the two bands?
Yeah, what I mean here is some sort of an average.
Okay.
The Urbach tail is usually some exponential decay, and so when you look at the barrier height, this barrier height is kind of defined as some average over the current which is injected. So you're absolutely right. It's not sharp.
Okay, thank you.
Sure. Okay. Another effect, going back to short-range interactions, though, another important process is electron-electron interaction, but now interband. So it's an interband short-range electron-electron interaction in which you have a high-energy electron in a conduction band, scattering with some electron in a valence band, and losing energy to this electron. This energy scale is not drawn. This energy is not drawn to scale. I mean, I have to conserve energy and momentum in drawing this plot. I'm not sure I've done the good thing. And anyway, so the electron, the partner electron, is excited across the gap to a state in a conduction band, while the primary electron drops down to a low energy state in a conduction band. And the net effect is that one electron now results in a generation of an electron, a new electron hole pair, plus a recoil electron, which is the same guy that we had before. You must have energy conservation. In this expression, this E sub C and E sub V are the kinetic energy in a conduction and valence band. So this E sub V actually is measured as increasing positive and increasing going down. The conduction band energy EC is measured from the bottom of the conduction band and increasing going up. Okay, that's why there is a gap here. We can write it in many different ways as long as we understand what it is. K1 and K1 prime are the wave vector of the initial electron and the final electron state, and K2 the same for the partner electron. And this clearly will be represented as a whole. And you have also must have conservation of crystal momentum, which means that the initial momentum is equal to the sum of all of the wave vectors of crystal momenta, all of the other particles, up to a wave vector, the reciprocal lattice, that actually in indirect gap materials plays a big role. In indirect gap material, the momentum conservation must be accompanied by some, either a G vector that moves you from this point to this point, or whatever K vector you have, might be phonon assisted, but Umland processes also can give you a large number of processes that can happen, particularly in indirect gap materials near threshold. And I'll discuss it in a bit more. So this direct process, direct gap materials, usually it's dominated by normal processes, which is when this G is equal to 0. In a case of parabolic bands, you can do the calculation analytically, assuming energy and momentum conservation. In indirect gap materials, things are much trickier, and their Umland processes play a major role because of the many Gs that you can have. Think of silicon when you go from the gamma point, which is the top of the valence band, excuse me, to the 6 ellipsoids, and then to the X point. There are big wave vectors connecting the two. So Umland processes can actually be extremely important and can give you processes which are all over the Brillouin zone, rendering momentum conservation kind of negligible, ironically. So a quick synopsis of what people have done. There is a long controversy about this. I mean, we go back from the early calculations done by Shockley himself, by Jean Baraf, Wolf. These are 1950s, 50s and 60s. There is a relatively recent controversy involving Capasso and Hess, whether in 3-5 compound semiconductors, the threshold for impact ionization is hard or soft, and that relates to the fact that we have direct gap materials. We expect sort of a hard threshold compared to the soft umklapp and phonon-dominated processes that we have in indirect gap materials. There are big issues. It's a complicated four-state process like the normal electron-electron interaction, but now umklapp processes can play a big role, and actually in indirect gap materials can use what's called the random K approximation, in which the large number of umklapp processes can lead you to satisfy momentum conservation. You can essentially ignore it. There are so many G's that you can involve that this process this condition or this constraint is irrelevant. The reason is that at large G vectors, the screening to the valence electron gets weak, so the interaction does not decay as quickly with increasing number of G vectors as you might expect. And this is the reason why this approximation actually works quite well. In parabolic direct gap materials, actually you can do the calculations analytically. I think the pioneering paper was due to Keldysh. There was some paper even before 1965. I think there was one in 1961. But anyway, he dealt with the ionization coefficient, which is at a given electric field, how many electron hole pairs are generated per unit length, per unit time, or per unit length, I should say. You can do the calculation analytically when you assume isotropic bands and a direct gap. Keldysh actually did not use isotropic bands, so his calculations, his results are kind of complicated by the unusual notation that goes back to the Russian notation and the time at which the paper was written, and the fact that he used different effective masses and he considered anisotropic values. Anyway, for a purely the ideal case of the effective mass of holes and electrons in the valence and conduction band, the same, you get that the threshold that is implied by energy and momentum conservation is 3/2 the gap. The reason why you cannot have impact ionization at the threshold of a gap is because if an electron goes back from its own state to the minimum of the conduction band, he will have to lose momentum, and a hole, an electron cannot be excited at exactly the gap energy at zero momentum, otherwise you would not conserve momentum. So there is a link between the minimum energy that is required to satisfy energy and momentum conservation, and the ratio of the effective masses. It happens to be 3/2 when these two are the same. The ionization rate that Keldysh calculated was some power of the energy above the threshold energy, normalized to the threshold energy itself, that happens to be 2 in this particular case of equal effective masses, and the constant in front, which has the dimension of 1 over time. Childs and Dyke in 1999 recently used the random K approximation in indirect materials, showing that if you ignore momentum conservation, it's a relatively simple calculation to do. It's only the joint density of states, so to speak, and you have a 7/2 power of the same expression. P has been a matter of controversy and what you should use. It's related, of course, to the Coulomb matrix element that you have averaged over all of the states that you have in your first-born approximation calculation. It's related to the band anisotropy, and it's related to what happens, how electrons can reach the threshold energy. In particularly, Brian Ridley proposed what's called the lucky drift model, in which he assumed that an electron travels, the electrons that ionize are those lucky electrons that survive an acceleration from zero energy to the threshold energy at a given field without suffering on any electron-phonon interaction, any losses to electron-phonon. So essentially this P in Ridley's lucky drift model becomes proportional to the square matrix element that you have, We'll talk a little bit more about it. And the scattering rate, the electron phonon scattering rate at the threshold energy. The matrix element. Boy, this is complicated more than the discussion we did about electron-electron interaction, because now the energies involved are very high. Threshold energy for silicon, 3/2 the gap, which is actually a little bit less than that, but it's at least one electron volts. For gallium arsenide, maybe more than 1.5. So the energy that we're dealing with, and can be even higher when ionization really dominates, begins to enter a range that corresponds to frequencies in which valence electrons may matter. Not surprisingly, because now you can have interband transitions that has to be included in order to calculate the dielectric response. So dielectric screening is a big issue. In indirect materials, you have phonon-assisted processes. They're higher order, but higher order when you do not have a direct process. So small compared to zero is big in a way. So they may matter. Okay, so you may see some temperature dependence near threshold. Again, the process is exactly the same matrix element that we discussed before for the electron-electron interaction, except that now there's no distribution function of the partner electrons. We're assuming that we're summing over all states which are full in a valence band and empty in a conduction band. So no factors of 1 minus f of k prime and 1 minus f of p prime, and no integration over the partner electrons. We're assuming that we're integrating over all electrons in the valence band. Again, the matrix element is the same, because after all we're dealing with electron-electron interactions, and we can do and perform the same approximation that we calculated before. We have a direct and an exchange Coulomb matrix element in which the energy lost or gained by the electron is different. This electron may go from 1 to 2 prime, and this electron from 2 to 1 prime in exchange process, which I haven't pictured, but of course it happens also here. You can do the full thing. You have to account for, and that becomes quite important now, the overlap factor we usually tend to ignore. In this case, the states of K and K prime, P and P prime are very different. They may be overlap factors between conduction and valence states, and between conduction states to conduction states, but at very different K points. So this may matter quite a bit. Okay, and so it's another beyond the case of optical transitions, which I guess at this point we'll discuss next week, concluding these sections, can be quite important. Screening is an issue. Here is the expression for the screening in the RPA that I gave you before, and in a valence band, this begins to be an energy, which is the exchange energy between the two electrons. This is big, so this can peak at a value which is at h bar omega, which is quite large, can be quite an effect. I will not go into details, but this is something that has been studied at length in order to see how to screen the electron phonon, the matrix element for this case. Anyway, I'll show you some results about the impact ionization that one can calculate using empirical pseudopotential band structure in a so-called constant matrix element approximation, in which essentially the Coulomb matrix element, the full matrix element accounting for spin singlet and spin triplet states, or exchange and direct, is essentially something which is a Q, the wave vector which is exchanged, is of the order of the inverse lattice constant, and some number which is of the order of unity. And then you can calculate essentially the impact ionization rate, assuming, considering a careful dynamic, kinematics of the interaction. So not the dynamics, which is represented by the matrix element, but by whatever is the so-called complicated joint density of states that you might have, and summing over the G vectors, comparing what you get by accounting for momentum conservation, but all UMCLA processes, and also using the random K approximation that Kane suggested, that is equivalent to ignoring momentum conservation, because the sum over the G vectors is it gives you so many states. Essentially, each of these G vectors give you a spike in a brittle end zone where momentum is conserved, and you have to sum over so many spikes that you can take an average over the entire brittle end zone and be done with it, ignoring momentum conservation. So this is the random K approximation, and let me just show you the results. These are calculated also by other groups. This is the group at Osaka University. This was a calculation done, boy, I forget, I think it was Washington State University or Oregon, I don't remember. And you see how in silicon the threshold is a little less than 3/2 the band gap. And whether you use the random K or the full ab initio calculation or the full constant matrix element calculation, you don't get much of a difference. The little squares are actually the ab initio calculation that represents some density of state issues that were obtained by Kolnick, but we couldn't reproduce them. So for holes, the issue is a little messier. You see that the threshold is a little less sharp. For gallium arsenide, I don't have the plots here, but the threshold is equally sharp. So you see that you can represent the expression with a power law, which is not too different from the 7/2 that was suggested by Childs, and because I should have shown it, I forget, maybe I'll post it in and I'll discuss it briefly next time, what happens for gallium arsenide compared to other calculations. And you can use those expressions to calculate the impact ionization coefficients, and you see that you get a relatively good agreement with at least some experimental data, although there are some disagreements about the impact ionization coefficients. The study of the problem goes back to the early days. 1954 is the early paper by Wolf, and William Shockley and Jean Baraf did a lot of contribution. These are models which I think are still used today with more sophisticated models. Okay, I think I will need more than 15 minutes to talk about radiative transition. So for today, I will stop here. I will take any questions. Next time we will finish up. I promise that I will post the ionization rates that we calculated for gallium arsenide and indium arsenide to show the difference that we get with respect to indirect gap materials. And having done that, we'll go through the radiative transitions, and then we will move finally to formulating transport, electronic transport in a theoretical way, before going into describing how we can solve it, how we can reduce it to semi-classical formulation and method of solutions, which will be what we'll discuss in the next month, which I think is the last month we have of our classes. So, any questions about what we've done? No questions? Again, all of you, please feel free to send me email, chats on Teams, although I had to stay logged on my Teams account at here UT Dallas during the week. But feel free to ask me any questions. If there are things which are not clear, please ask me, okay? If there is nothing else, then have a good weekend, get vaccinated, survive COVID, and I'll show you next week.
Ciao Massimo.
Bye-bye. Ciao Massimo.
Ciao.
Ciao ciao.